In the vast, silent theater of our solar system, a cosmic drama unfolds, a play billions of years in the making. The stage is set with a single, radiant star, and the actors are four unique worlds, each with its own story to tell. It's a story of creation, destruction, and ultimately, the delicate balance that allows life to flourish. We are about to embark on a journey through this celestial neighborhood to witness the contrasting fates of these planetary siblings. Prepare to be amazed by the sheer scale of time and space, and by the subtle forces that have shaped these worlds into what they are today. Four rocky worlds perform an ancient cosmic dance around a central star, a ballet choreographed by gravity and time. Each orbit, a carefully measured path, dictates the amount of energy received from the sun, a crucial factor in determining a planet's destiny. These aren't just lifeless rocks, they are dynamic systems, constantly evolving and interacting with their environment. Their movements, seemingly simple, are the result of complex gravitational interactions that have shaped their orbits over billions of years. These are the inner planets, the terrestrial quartet, the rocky core of our solar system's family. They stand in stark contrast to their gaseous giant siblings further out, each a testament to the diverse possibilities of planetary formation. Mercury, Venus, Earth, and Mars. They are a family, forged from the same stellar nursery, a swirling cloud of gas and dust where stars are born and planets begin to coalesce. Imagine the chaos and energy of that early solar system, a cosmic crucible where the building blocks of worlds were forged in the heart of a nebula. It was a time of intense bombardment, of collisions and mergers, as these nascent planets struggled to find their place in the solar system. Born of the same dust and gas that swirled into existence 4.6 billion years ago, a cosmic recycling process then repeating throughout the universe for eons. This primordial soup contained all the elements necessary for life, the very atoms that make up our bodies and the world around us. It's a humbling thought to realize that we are all, in a sense, stardust, remnants of long-dead stars that seeded the universe with the building blocks of life. They are siblings, bound by a shared origin story, a common heritage that stretches back to the very beginning of our solar system. They share the same parent star, the same raw materials, and the same initial conditions. Yet, despite these similarities, their destinies have diverged in remarkable ways. Yet each has followed a dramatically different path, a testament to the complex interplay of factors that determine a planet's fate. What forces drove these worlds down such divergent paths? What lessons can we learn from their successes and failures? These are the questions that drive our exploration of these fascinating worlds. Their stories are etched across their surfaces in the form of impact craters, volcanic plains, and ancient riverbeds. Each geological feature tells a tale of past events, of cataclysmic collisions, volcanic eruptions, and the slow, relentless forces of erosion. By studying these surface features, we can piece together the history of each planet and understand the processes that have shaped them over billions of years. Hidden in their atmospheres, in the swirling clouds, the chemical composition, and the temperature profiles. Atmospheres act as planetary shields, regulating temperature, protecting from harmful radiation, and distributing heat around the globe. The presence or absence of an atmosphere, its density and composition, can dramatically alter a planet's surface conditions and its potential for habitability, and locked deep within their metallic hearts, in the churning molten iron that generates magnetic fields and drives volcanic activity. The internal structure of a planet, its core, mantle, and crust, plays a crucial role in its evolution. The presence of a molten core can generate a magnetic field which protects the planet from harmful solar radiation. Volcanic activity can release gases into the atmosphere, shaping its composition and influencing the planet's climate. This is the tale of four worlds, once so alike, sharing a common ancestry and a similar starting point in the grand cosmic race. In their youth, they may have all possessed oceans, atmospheres, and the potential for life. But as time marched on, their paths diverged, leading them to their current, dramatically different states. Now profoundly, and sometimes mysteriously, different, each a unique experiment in planetary evolution. The differences between these worlds are not just superficial. They reflect fundamental differences in their internal processes, their atmospheric dynamics, and their interactions with the Sun and the rest of the solar system. Their individual journeys tell a larger story about the forces that shape planets across the cosmos, providing valuable insights into the processes that govern planetary formation and evolution throughout the universe. By studying these four worlds, we can gain a better understanding of the conditions that are necessary for life to arise and the factors that can lead to planetary demise. This knowledge is crucial as we search for habitable planets beyond our solar system. Imagine four seeds planted in the same garden, receiving light from the same sun, sharing the same soil, and yet growing into vastly different plants. What accounts for these differences? What subtle variations in their environment or their own internal makeup led them down such divergent paths? One grows into a barren, scorched rock, a desolate world baked by the relentless heat of the sun. Its surface is scarred by countless impact craters, a testament to the constant bombardment it has endured over billions of years. It's a world of extremes, where temperatures swing wildly from scorching hot during the day to frigidly cold at night. Another becomes a toxic, suffocating inferno, a hellish landscape shrouded in thick, poisonous clouds. Its atmosphere is so dense that it crushes any spacecraft that dares to venture too close to the surface. The temperature is hot enough to melt lead, and the air is filled with noxious gases that would be instantly fatal to humans. A third blossoms into a vibrant, living oasis teeming with complexity, a blue marble suspended in the vastness of space. Its surface is covered with vast oceans, lush forests, and towering mountains. Its atmosphere is breathable, its temperature is moderate, and its surface is teeming with life in all its incredible diversity. And the fourth withers into a cold, red desert, a ghost of its once watery past, a tantalizing reminder of what might have been. Its surface is dry and dusty, its atmosphere is thin and cold, and its landscape is scarred by ancient riverbeds and canyons, hinting at a time when water flowed freely across its surface. This is the story of our cosmic neighborhood, a tale of four worlds, four destinies, and the forces that shaped them all. It's a story that is both fascinating and cautionary, offering valuable insights into the delicate balance that makes a planet habitable and the factors that can lead to its demise. Mercury, the scorched seed, a planet perpetually caught in the sun's fiery embrace. Its proximity to our star has made it a world of extremes, a place where the sun's radiation relentlessly bombards its surface. Hugs the sun so tightly it exists in a state of perpetual extremes, a world of scorching days and freezing nights, a testament to the power of solar radiation and the lack of a protective atmosphere. The temperature difference between the sunlit side and the shadowed side is immense, creating a harsh and unforgiving environment. Venus, the toxic twin, a world shrouded in mystery and veiled by a thick, impenetrable atmosphere. Its beauty is deceptive, hiding a surface that is anything but hospitable, shrouded itself in a thick, poisonous blanket that traps heat relentlessly, creating a runaway greenhouse effect that has turned it into a scorching hellscape. The atmosphere is composed primarily of carbon dioxide, a potent greenhouse gas, which traps solar radiation and raises the surface temperature to unbearable levels. Mars, the withered world, a planet that once held the promise of life, now a cold, red desert, a shadow of its former self. Its story is a cautionary tale of atmospheric loss and the consequences of a weakening magnetic field. Lost its protective atmosphere and its flowing waters, leaving behind only tantalizing clues of what might have been: ancient riverbeds, dried-up lake basins, and subsurface ice deposits. These features suggest that Mars was once a much warmer and wetter place, a planet that may have even harbored life. And then there is Earth, our home, the blue planet, the living world, a beacon of life in the vast emptiness of space. It is a planet that we know intimately, yet still holds countless mysteries waiting to be uncovered. The vibrant blue marble that stands as the extraordinary exception in this planetary family, a testament to the rare and delicate balance of conditions that are necessary for life to arise and thrive. Its existence is a constant source of wonder and a reminder of the preciousness of our own planet. It is a world alive, a planet where chemistry became biology, where simple molecules self-assembled into complex organisms, and where life has flourished for billions of years. It is a planet that is constantly evolving, shaped by the forces of nature and the ever-increasing influence of humanity, where oceans teem with life and continents drift across a molten mantle driven by the forces of plate tectonics. This dynamic geology is essential for regulating the Earth's climate and recycling essential nutrients for life. The movement of continents has shaped the Earth's surface over millions of years, creating mountain ranges, ocean basins, and volcanic islands. Its uniqueness is not just a matter of pride, it is a profound scientific puzzle, a question that has captivated scientists for centuries. What makes Earth so special? What combination of factors allowed life to take root and flourish on this planet, while its siblings remained barren and lifeless? Why here? Why did life take root on this world and, as far as we know, nowhere else in our solar system? Is Earth a unique anomaly, or are there other planets out there that harbor life waiting to be discovered? These are the questions that drive our search for extraterrestrial life. The answer is not simple. There is no single factor that explains Earth's habitability. Instead, it is a complex interplay of many different factors, each contributing to the overall balance that allows life to thrive. It is a complex tale involving just the right distance from the sun, providing the perfect amount of energy for liquid water to exist on the surface, the presence of a large moon, stabilizing Earth's axial tilt and preventing extreme climate variations, a protective magnetic field, shielding the planet from harmful solar radiation, and a dynamic geology that recycles essential ingredients for life, such as carbon and water. To truly understand our own world, we must look beyond its blue horizons to compare and contrast it with its planetary siblings. By studying the similarities and differences between these worlds, we can gain a deeper understanding of the factors that make Earth so unique. We must journey to its siblings to explore their surfaces, analyze their atmospheres, and probe their interiors. Only by venturing beyond our own planet can we truly appreciate the delicate balance that makes Earth habitable. By visiting the scorched plains of Mercury, we can learn about the effects of extreme solar radiation and the challenges of surviving in a harsh, airless environment. The crushing pressures of Venus, we can understand the runaway greenhouse effect and the dangers of unchecked atmospheric warming. And the frozen canyons of Mars, we can explore the mysteries of atmospheric loss and the potential for past or present life on the red planet. We gain a new perspective on Earth, a deeper appreciation for its unique qualities, and a greater understanding of the forces that have shaped its destiny. Comparative planetology allows us to see our own planet in a new light, to understand its place in the solar system and its potential future. These worlds are not just distant points of light in our night sky, they are natural laboratories, offering invaluable opportunities to study planetary processes in action. Each planet is a unique experiment, shaped by different initial conditions and subjected to different environmental forces. They are case studies in planetary evolution, showing us what can happen when a planet's delicate balance is tipped one way or another, when a critical threshold is crossed, and when a planet's destiny is irrevocably altered. By studying these case studies, we can learn valuable lessons about the factors that contribute to planetary habitability and the dangers that can lead to planetary demise. Their stories are our stories, reflecting the past and potential futures of rocky worlds, including our own. They offer a glimpse into the possible fates that await Earth, depending on the choices we make and the actions we take to protect our planet. This journey is more than an exploration of space. It is a quest for self-knowledge, a search for our place in the universe, and a deeper understanding of the forces that have shaped our world and our destiny. It is a journey that will challenge our assumptions, expand our horizons, and ultimately help us to better appreciate the preciousness of life on Earth. The story of these four worlds, Mercury, Venus, Earth, and Mars, begins not with solid ground or serene skies, but in fire and chaos. It's a tale etched in the very fabric of the cosmos, a narrative of creation and transformation played out on a grand scale. We're about to journey back to a time when these familiar planets were nothing more than swirling clouds of gas and dust, caught in the tumultuous dance of a nascent solar system. Prepare to witness the raw power of stellar birth and death, the relentless pull of gravity, and the delicate balance of forces that ultimately shape the destinies of these four unique worlds. It starts 4.6 billion years ago, long before the planets themselves existed, before the familiar constellations adorned the night sky, and before life had even begun to dream of existence. This is a story of deep time, a period when the solar system was a chaotic nursery, a place of immense energy and unimaginable potential. We're talking about a time when the very building blocks of our world were being forged in the heart of a stellar furnace, a time when the laws of physics were the only architects at work. There was only a vast, cold cloud of interstellar gas and dust, a cosmic reservoir of raw materials stretching across unimaginable distances. This cloud, a swirling mix of hydrogen, helium, and heavier elements, was the legacy of countless generations of stars that had lived and died before our sun was even a glimmer in the cosmic dark. It was a place of quiet potential, a slumbering giant waiting for the right moment to awaken, a nebula left over from the death of an ancient star. This stellar ancestor, in its final act of cosmic drama, had seeded the surrounding space with the very elements that would eventually form our planets, our bodies, and everything we know. Its death was not an end, but a beginning, a cosmic recycling event that paved the way for a new generation of stars and planets. The nebula was a testament to the interconnectedness of the universe, a reminder that everything is made of stardust. A nearby cosmic event, perhaps the shockwave from a supernova, a cataclysmic explosion marking the death of a massive star, sent ripples through the interstellar medium. This wasn't just any disturbance. It was a cosmic wake-up call, a jolt of energy that would forever alter the fate of our solar system. The supernova's shockwave acted like a cosmic hand, squeezing and compressing the vast cloud of gas and dust, disturbed this placid cloud, causing it to collapse under its own gravity. The once diffuse cloud began to coalesce, its particles drawn together by the irresistible force of mutual attraction. As the cloud contracted, its density increased, and the pull of gravity grew stronger, accelerating the collapse. This was the beginning of a runaway process, a cosmic avalanche that would ultimately lead to the birth of our sun and the formation of the planets. As it collapsed, it began to spin, slowly at first, but with increasing speed as the cloud shrank in size. This rotation was a consequence of the conservation of angular momentum, a fundamental law of physics that dictates that a spinning object will spin faster as it gets smaller. Imagine a figure skater pulling their arms in during a spin. The same principle applies to the collapsing nebula, flattening into a massive, rotating disk. This disk, known as a protoplanetary disk, was a swirling vortex of gas and dust, a cosmic pizza dough being spun into shape. It was within this disk that the planets would eventually form, like seeds germinating in fertile soil. The disk was a dynamic and chaotic environment, a place of constant collisions, mergers, and transformations. At the center of this swirling vortex, pressure and temperature soared, reaching unimaginable levels as the collapsing material became increasingly compressed. Atoms were stripped of their electrons, creating a superheated plasma, a state of matter where particles are ionized and move at incredible speeds. This was the crucible where the sun would be forged, the heart of our solar system, about to ignite, until the core ignited in nuclear fusion. Hydrogen atoms, under immense pressure and temperature, were forced to fuse together, releasing tremendous amounts of energy in the process. This was the moment of stellar birth, the ignition of a nuclear furnace that would power our solar system for billions of years to come. The sun was born, a beacon of light and heat in the cosmic darkness. Our sun was born, a young and energetic star, far brighter and more active than it is today. It was a time of intense radiation and powerful solar flares, a period of cosmic adolescence for our star. The sun's birth marked a turning point in the history of our solar system, the beginning of a new era of planetary formation and evolution, bathing the nascent solar system in light and heat for the very first time. The once dark and cold protoplanetary disk was now illuminated by the sun's radiant energy, transforming the environment and setting the stage for the formation of planets. This was the dawn of a new solar system, a place of immense potential and untold possibilities. This young, radiant sun acted as a great cosmic sorter, a celestial gatekeeper, determining which materials could survive in different regions of the protoplanetary disk. Its energy sculpted the environment, creating distinct zones with varying temperatures and compositions. The sun's influence was paramount, shaping the destinies of the planets that would eventually emerge. Its intense heat created a temperature gradient across the protoplanetary disk, a gradual decrease in temperature as you moved farther away from the sun. This temperature gradient was crucial in determining the composition of the planets that would form in different regions of the disk. It was a cosmic thermostat, regulating the distribution of materials and influencing the planetary architecture of our solar system. Close to the star, where the inner planets would form, in the scorching heat of the sun's embrace, conditions were harsh and unforgiving. Only the most resilient materials could withstand the intense radiation and high temperatures. This inner region was a crucible, forging planets from the remnants of stellar creation. It was too hot for volatile materials like water ice, the stuff of comets and distant moons, to exist in solid form. The sun's heat caused these volatile compounds to evaporate, turning them into gases that were quickly swept away by the solar wind. This left behind a barren landscape, devoid of the icy building blocks that would be abundant in the outer solar system, and methane to condense into solids. These volatile compounds, essential for life as we know it, were simply unable to survive in the extreme heat of the inner solar system. The molecules that make up water and methane were broken apart by the sun's energy, preventing them from forming the icy grains that could have contributed to planet formation. Only materials with high melting points, such as rock, the silicates and minerals that make up the Earth's crust, could endure the sun's relentless heat. These refractory materials, able to withstand extreme temperatures without melting or vaporizing, became the primary building blocks of the inner planets, and metal, iron, nickel, and other heavy elements forged in the hearts of dying stars could endure. These metallic elements, dense and resilient, played a crucial role in the formation of planetary cores, providing the gravitational foundation upon which the inner planets would be built. This region became the domain of the terrestrial planets, the rocky worlds of Mercury, Venus, Earth, and Mars. These planets, forged from the remnants of stellar creation, would forever be defined by their proximity to the sun and their composition of rock and metal. Farther out, beyond a boundary known as the frost line, a critical threshold in the protoplanetary disk, the environment was drastically different. This invisible line marked the point where temperatures dropped low enough for volatile compounds to freeze into solid ice. Temperatures were low enough for ices to form. Water ice, methane ice, ammonia ice, all these volatile compounds, banished from the inner solar system, could now condense into solid form, creating a vast reservoir of icy building blocks. This allowed the outer worlds, Jupiter, the king of the planets, to accumulate vast amounts of icy material, providing the foundation for its immense size and gravitational influence. Jupiter's formation was a pivotal event in the history of our solar system, shaping the orbits of other planets and influencing the distribution of asteroids and comets. And Saturn, to grow into gas giants, behemoths of the outer solar system, dwarfing the terrestrial planets in both size and mass. These gas giants, with their swirling atmospheres and complex ring systems, represent a fundamentally different type of planet than their rocky counterparts in the inner solar system. Their immense gravity capturing vast envelopes of hydrogen, the lightest and most abundant element in the universe, from the surrounding protoplanetary disk. This accretion of hydrogen gas allowed Jupiter and Saturn to grow to their enormous sizes, becoming the dominant gravitational forces in the outer solar system, and helium from the surrounding disk. These two gases, the primary constituents of the Sun, formed the bulk of Jupiter and Saturn's atmospheres, creating the swirling cloud patterns and vibrant colors that we observe today. The gas giants are essentially miniature versions of the Sun, albeit without the nuclear fusion at their cores. Within this inner, rocky domain, the process of accretion began, the slow and steady accumulation of dust and gas into larger and larger bodies. This was a bottom-up process, starting with microscopic particles and gradually building up to planet-sized objects. It was a slow, patient construction project spanning millions of years, a cosmic ballet of collisions and mergers, guided by the laws of gravity and electromagnetism. The formation of the terrestrial planets was not a quick and easy process. It was a long and arduous journey, fraught with peril and punctuated by cataclysmic events. Microscopic dust grains, forged in the hearts of long-dead stars, the remnants of supernova explosions, and the stellar winds of red giants, were the raw materials for planet formation. These tiny particles, composed of silicates, metals, and other elements, were the seeds from which the planets would grow, began to stick together through electrostatic forces, the same forces that cause static cling in your clothes. These weak but persistent forces allowed the dust grains to overcome their initial inertia and coalesce into larger aggregates. Clumps grew into pebbles, small rocky aggregates ranging in size from millimeters to centimeters. These pebbles, like cosmic gravel, were the next step in the planet-building process. Pebbles collided to form rocks, larger and more substantial building blocks, ranging in size from centimeters to meters. These rocks, like cosmic cobblestones, were the foundation upon which the planets would be built. And rocks smashed together to create planetesimals, small, asteroid-sized bodies ranging in size from kilometers to hundreds of kilometers. These planetesimals were the first true planetary embryos, the seeds of the worlds that would eventually emerge, the building blocks of planets. These planetesimals, like cosmic Lego bricks, were the fundamental units of planetary construction. They were the raw materials that would be assembled through countless collisions and mergers into the planets we know today. These city-sized bodies orbited the young sun in a chaotic swarm, a swirling mass of planetesimals, constantly colliding and interacting with each other. This was a period of intense gravitational chaos, a cosmic demolition derby where only the strongest and luckiest planetesimals would survive, their paths inevitably crossing. The crowded conditions in the protoplanetary disk meant that collisions were frequent and unavoidable. These collisions could be either destructive, shattering the planetesimals into smaller fragments, or constructive, merging them into larger bodies. The journey from dust to planet was a violent one, a cosmic struggle for survival where only the fittest would prevail. The early solar system was a dangerous place, a shooting gallery of planetesimals constantly bombarding each other, marked by cataclysmic collisions, giant impacts that reshaped the surfaces of the growing planets and even created new worlds. These collisions were not gentle taps. They were titanic events that released enormous amounts of energy, melting rock and vaporizing entire oceans. That either shattered the growing worlds, breaking them apart into fragments that would either be ejected from the solar system or reaccrete into new bodies. These destructive collisions were a major obstacle to planet formation, preventing some planetesimals from ever reaching full planetary size, or merged them into even larger bodies, a process known as accretionary growth, where smaller planetesimals gradually accumulated mass by colliding and merging with each other. This process allowed some planetesimals to grow into protoplanets, the precursors to the planets we know today. Out of this cosmic demolition derby, 4 primary survivors emerged, 4 protoplanets that managed to avoid catastrophic collisions and successfully accrete enough mass to become fully fledged planets. These 4 survivors would become the inner terrestrial planets of our solar system: Mercury, Venus, Earth, and Mars. These 4 worlds, each unique and fascinating in its own way, share a common origin in the protoplanetary disk that surrounded the young sun. They are our closest neighbors in the vast expanse of space, and they hold clues to the formation and evolution of our own planet. They were all born from the same rocky and metallic materials, the same stardust that had been swirling around the sun for millions of years. Their composition reflects the conditions in the inner solar system, where volatile compounds were scarce and refractory materials were abundant, in the same neighborhood of space at roughly the same time. They are siblings, born from the same cosmic womb, sharing a common heritage and a shared destiny. Their proximity to each other and to the sun has shaped their evolution in profound ways. Their shared origin is the very thing that makes their current diversity so compelling. Despite starting from similar ingredients and in similar locations, These 4 planets have diverged dramatically over the past 4.5 billion years. They are a testament to the power of chance and the complexity of planetary evolution. It presents us with a profound cosmic experiment, a natural laboratory where we can study the factors that influence planetary evolution and the conditions that make a planet habitable. By comparing and contrasting these 4 worlds, we can gain a deeper understanding of our own planet and its place in the universe. If these 4 worlds started with such similar ingredients, with the same basic building blocks and in the same general location, it begs the question: what forces drove them down such different paths? What factors determined whether a planet would become a scorching hellhole, a frozen wasteland, or a vibrant oasis of life? What steered them down such radically different evolutionary highways? What were the key turning points, the critical moments that determined their ultimate fates? The answers to these questions lie in a complex interplay of factors, some predictable and some entirely random. The answers lie in the subtle differences in their size, their mass, and their gravitational pull. A planet's size determines its ability to retain an atmosphere, to generate a magnetic field, and to drive geological activity. Larger planets tend to be more geologically active and have thicker atmospheres, while smaller planets tend to be geologically dead and have thin or no atmospheres. Their distance from the Sun, the amount of solar radiation they receive, and the resulting temperature of their surfaces. Planets closer to the Sun are hotter and drier, while planets farther away are colder and icier. The distance from the Sun also affects the composition of a planet's atmosphere and the stability of liquid water on its surface, and a healthy dose of cosmic chance, random events such as asteroid impacts, volcanic eruptions, and changes in solar activity that can dramatically alter a planet's climate and environment. These chance events can act as wildcards, pushing a planet down one evolutionary path or another, factors that would ultimately determine whether a world would become a hellscape, a frozen desert, or a living paradise. The story of Mercury, Venus, Earth, and Mars is a story of planetary divergence, a tale of how small differences in initial conditions and random events can lead to vastly different outcomes. It's a story that reminds us of the delicate balance of forces that make our own planet habitable and the importance of understanding the factors that can threaten its future. As we stand on the precipice of this interplanetary journey, poised to explore the vast expanse of our solar system and perhaps one day venture beyond, it's natural to reflect on the unique place we call home. We're about to embark on a quest to understand the cosmos, but before we do, let's take a moment to appreciate the extraordinary planet that birthed us. One question echoes louder than any other, a question that has captivated scientists, philosophers, and dreamers for centuries. It's a question that delves into the very essence of our existence and our place in the universe. What makes Earth so special? What confluence of factors has allowed this particular planet, among the countless others in the cosmos, to become a haven for life? What is it about our world that sets it apart, making it not just habitable, but teeming with a biodiversity that continues to astound and inspire? From the cold vacuum of space, a perspective that offers both humbling insignificance and profound beauty, our planet is an unmistakable jewel. A vibrant sphere of blues, greens, browns, and whites, swirling in a cosmic dance. It beckons us to understand its secrets, to decipher the code that has allowed life to flourish. It is a world of breathtaking dynamism, a constantly evolving tapestry of natural processes. From the shifting of tectonic plates to the ebb and flow of tides, Earth is a planet in perpetual motion, where blue oceans slosh against green and brown continents, creating coastlines that are as diverse as they are beautiful. These vast bodies of water are not just scenic features, they are the cradles of life, the nurseries of countless species, and the regulators of our planet's climate. And swirling white clouds dance across a transparent atmosphere, a protective blanket that shields us from harmful radiation and regulates the temperature, creating a habitable environment. These clouds are more than just picturesque formations. They are integral to the water cycle, distributing life-giving rain across the globe. This living, breathing quality is a testament to the intricate interplay of geological, chemical, and biological processes that have shaped our planet over billions of years. It's a symphony of interactions, a delicate balance that sustains life as we know it. As far as we can tell, unique among its rocky siblings. While we continue to search for signs of life beyond Earth, our current understanding suggests that our planet holds a truly exceptional position in our solar system. Mercury is a silent, airless rock, a desolate world baked by the sun's relentless radiation. It's a stark reminder of the conditions that can exist in the absence of a protective atmosphere and a dynamic geology. Venus is a toxic oven, shrouded in a thick, suffocating atmosphere of carbon dioxide and sulfuric acid. Its surface temperature is hot enough to melt lead, a testament to the runaway greenhouse effect that has transformed it into an uninhabitable hellscape. Mars is a frigid, rusty wasteland, a once promising world that has lost its atmosphere and its liquid water. While there is evidence that Mars may have once been habitable, it is now a harsh and unforgiving environment. But Earth pulses with activity, a vibrant and dynamic planet that is constantly changing and evolving. Its surface is shaped by the forces of nature, from the slow creep of glaciers to the violent eruption of volcanoes. Its surface constantly reshaped not just by geological forces, but by life itself. From the formation of coral reefs to the growth of forests, living organisms play a crucial role in shaping the Earth's landscape. This is the central mystery we seek to unravel. How did Earth become so different from its neighbors? What are the key ingredients that have allowed life to not only survive, but to thrive on our planet? The most obvious answer lies in our planet's location, its position within the solar system. But as we'll see, location is just one piece of the puzzle. There are other factors at play, subtle but crucial elements that have conspired to make Earth the unique and habitable world that it is. Earth orbits the Sun within a region known as the habitable zone, a region of space where conditions are potentially suitable for liquid water to exist on a planet's surface. This zone is not a fixed boundary, but rather a range of distances from a star where the temperature is neither too hot nor too cold. Often nicknamed the Goldilocks zone, a whimsical but apt description that captures the idea of a just right environment. It's a place where the conditions are not too extreme, but rather conducive to the development and sustenance of life. This is the narrow band of space around a star, a cosmic sweet spot where the energy from the star is sufficient to warm a planet, but not so intense as to boil away its oceans. The exact location of the habitable zone depends on the size and temperature of the star. Where temperatures are just right, a delicate balance that allows water to exist in its liquid form. This is a crucial requirement for life as we know it, as liquid water plays a vital role in biological processes. Not too hot and not too cold, a Goldilocks scenario that avoids the extremes of scorching heat and frigid ice. This temperature range is essential for maintaining the stability of liquid water and allowing complex molecules to form and interact, for liquid water to exist on a planet's surface. This seemingly simple requirement has profound implications for the possibility of life. Without liquid water, the complex chemical reactions that underpin life as we know it would be impossible. Liquid water is the solvent of life as we know it, the universal medium in which biological molecules dissolve and interact. It's the lifeblood of our planet, the source of all the oceans, rivers, and lakes that support a vast array of ecosystems, the medium in which the complex chemistry of biology can unfold. It facilitates the transport of nutrients, the removal of waste products, and the regulation of temperature, all of which are essential for life to thrive. Venus orbits slightly too close to the Sun, a position that has had catastrophic consequences for its habitability. Its proximity to the Sun has led to a runaway greenhouse effect, transforming it into a scorching inferno. On the inner edge of this zone, where the Sun's radiation is intense enough to trigger a cascade of events that ultimately rendered the planet uninhabitable. It serves as a cautionary tale about the delicate balance required for a planet to remain habitable, where a runaway greenhouse effect boiled its oceans away, trapping heat and creating a dense, toxic atmosphere. This extreme example highlights the importance of a planet's atmosphere in regulating its temperature and maintaining its habitability. Mars orbits on the outer edge, a position that has also presented challenges to its habitability. Its distance from the Sun means that it receives less solar energy, making it a much colder planet than Earth, where a thinning atmosphere allowed its liquid water to freeze or escape into space, leaving behind a dry, desolate landscape. The loss of its atmosphere has also made Mars more vulnerable to solar radiation, further hindering its potential for life. But location alone is not the full story. While being in the habitable zone is a necessary condition for life, it is not a sufficient one. There are other factors that play a crucial role in determining a planet's habitability. Both Venus and Mars are, in some respects, within the broader boundaries of the habitable zone, meaning that they receive enough solar energy to potentially support liquid water. However, their actual conditions are far from ideal, yet they are profoundly inhospitable. Their atmospheres are either too thick or too thin, their surfaces are either too hot or too cold, and they lack the essential ingredients for life as we know it. Earth possesses other critical advantages, factors that go beyond its location in the habitable zone. These advantages are the result of a complex interplay of geological, chemical, and biological processes that have shaped our planet over billions of years. One is its size and mass, which are just right for maintaining a stable atmosphere and a dynamic geology. A planet's size and mass determine its gravitational pull, which in turn affects its ability to retain an atmosphere, which provide it with enough gravity to hold on to a substantial atmosphere and a hot molten core. This molten core is crucial for generating a magnetic field, which protects the planet from harmful solar radiation. This molten iron core generates a powerful magnetic field, a phenomenon known as the geodynamo. This magnetic field is not just a curiosity, it is a vital shield that protects our planet from the harsh environment of space, that extends far out into space, creating a protective bubble around the Earth. This bubble, known as the magnetosphere, deflects the solar wind and prevents it from stripping away our atmosphere, acting as an invisible shield, deflecting harmful particles and radiation away from the Earth's surface. Without this shield, life on Earth would be impossible. This magnetosphere deflects the solar wind, a constant barrage of charged particles emanating from the Sun. These particles can be harmful to living organisms and can also erode a planet's atmosphere over time. A constant stream of charged particles from the Sun, traveling at high speeds and carrying immense energy. If these particles were to reach the Earth's surface, they would wreak havoc on our atmosphere and our ecosystems that would otherwise strip away our atmosphere and bombard the surface with deadly radiation, making it impossible for life to exist. The magnetosphere acts as a crucial defense against this threat, protecting our planet and allowing life to flourish. A fate that likely befell Mars billions of years ago. Mars once had a thicker atmosphere and liquid water on its surface, but it lost its magnetic field, leaving it vulnerable to the solar wind. Furthermore, Earth has a dynamic geology driven by plate tectonics, a process that is unique among the rocky planets in our solar system. Plate tectonics plays a crucial role in regulating the Earth's climate and maintaining its habitability. The planet's crust is broken into massive plates that drift across the surface, driven by the heat from the Earth's interior. This movement is responsible for many of the Earth's most dramatic geological features, such as mountains, volcanoes, and earthquakes, colliding, separating, and sliding past one another, creating a dynamic and ever-changing landscape. These interactions release energy in the form of earthquakes and volcanic eruptions, which can have both destructive and constructive effects. This process is crucial for regulating the planet's climate over geological timescales, preventing extreme temperature fluctuations, and maintaining a stable environment for life. Plate tectonics helps to regulate the carbon cycle, which is essential for controlling the Earth's greenhouse effect. It recycles carbon, pulling it from the atmosphere and locking it into rocks through a process called carbon sequestration. This process helps to remove excess carbon dioxide from the atmosphere, preventing the planet from overheating. Preventing the climate from spiraling out of control like on Venus, where a runaway greenhouse effect has created a scorching and uninhabitable environment. Earth's plate tectonics acts as a natural thermostat, keeping the planet's temperature within a habitable range. It also drives volcanism, the eruption of molten rock and gases from the Earth's interior. While volcanic eruptions can be destructive, they also play a vital role in replenishing the Earth's atmosphere and releasing essential nutrients, which releases essential gases and nutrients back to the surface, enriching the soil and providing the building blocks for life. Volcanic eruptions also release water vapor into the atmosphere, which contributes to the formation of clouds and precipitation. Earth is not a static ball of rock. It is a dynamic and evolving planet, constantly shaped by the forces of nature and the influence of life. Its surface is a mosaic of diverse landscapes, from towering mountains to vast oceans, all interconnected and interdependent. It is a complex, interconnected system where every component plays a role in maintaining the planet's overall health and stability. The Earth's atmosphere, oceans, land, and life are all intertwined, influencing one another in countless ways, where geology, atmosphere, oceans, and life all influence one another in a delicate, life-sustaining dance. Understanding these complex interactions is crucial for protecting our planet and ensuring its habitability for future generations. The story of Earth is a story of interconnectedness, a testament to the power of collaboration and the delicate balance that sustains life. The study of other planets is not merely an exercise in cosmic curiosity, a pastime for stargazers and dreamers. It's not just about filling textbooks with facts about faraway worlds. It's so much more than that. It's a quest to understand our place in the universe, to unravel the mysteries of planetary evolution, and most importantly, to safeguard the future of our own precious home. We gaze at these distant orbs, not just to admire their beauty, but to glean vital clues about the forces that shape planets, the processes that govern their climates, and the delicate balance that allows life to flourish. It's actually a fundamental tool for understanding our own home. By studying these other worlds, we gain a unique perspective on Earth, allowing us to see it not as an isolated entity, but as one planet among many, subject to the same physical laws and evolutionary pressures. It's like holding up a mirror to our own world, revealing its strengths and weaknesses, its vulnerabilities, and its potential. This comparative approach allows us to identify the key factors that have made Earth habitable and to understand the threats that could jeopardize its future. By examining the divergent fates of our planetary siblings, Venus, Mars, and even Mercury, we gain invaluable insights into the range of possible outcomes for a planet's evolution. These worlds, once potentially similar to Earth, have followed different paths, leading to vastly different present-day conditions. Understanding why these planets diverged from Earth's trajectory is crucial for predicting our own planet's future and for mitigating the risks that could lead to a similar fate. We hold up a mirror to Earth. We see reflected in their stories the potential consequences of our actions, the delicate balance of our climate, and the importance of preserving the conditions that make our planet habitable. It's a cosmic reflection, a chance to learn from the successes and failures of other worlds and to make informed decisions about our own future. Approach, known as comparative planetology, is a powerful tool that allows us to move beyond simply describing individual planets and to begin to understand the underlying principles that govern their formation, evolution, and habitability. It's a holistic approach that considers the interconnectedness of planetary systems and the complex interplay of physical, chemical, and biological processes. Allows us to see our world in a broader context, not as a unique and isolated anomaly, but as one example of a planet within a vast and diverse population. By placing Earth within this broader context, we can better understand its place in the universe and appreciate the factors that have made it so special. We begin to see the Earth as a single point within a spectrum of possibilities, revealing the fragility of the conditions that make it habitable. The thin blue line of our atmosphere, the delicate balance of our climate, the presence of liquid water on our surface, these are all precious and precarious conditions that could easily be disrupted. Comparative planetology helps us to appreciate just how fortunate we are to live on a planet that has maintained these conditions for billions of years, and to understand the importance of protecting them for future generations. Each planet in the inner solar system offers a crucial lesson, a piece of the puzzle that helps us to understand the complex processes that shape planetary environments. They are laboratories in the sky, each one offering a unique perspective on the factors that influence habitability, a warning, or a glimpse into what might have been. They are not just lifeless rocks, but rather dynamic worlds with their own unique histories and stories to tell. By deciphering these stories, we can gain a deeper understanding of the past, present, and future of our own planet. They really are control groups in a grand experiment, a cosmic laboratory where the laws of physics and chemistry have been playing out for billions of years. Each planet represents a different experimental condition, a different set of initial parameters that have led to a unique outcome that's been running for over 4 billion years, a timescale that is almost incomprehensible to the human mind. Over these vast stretches of time, planets have formed, evolved, and transformed, their surfaces sculpted by geological processes, their atmospheres shaped by solar radiation, and their potential for life determined by a complex interplay of factors. And the results are written in their geology and atmospheres. The rocks, the craters, the mountains, the clouds, the gases, all of these features are clues that tell a story about a planet's past. By carefully analyzing these clues, scientists can reconstruct the history of a planet and understand the processes that have shaped it over billions of years. Venus, for example, serves as a stark cautionary tale, a warning about the dangers of unchecked greenhouse gas emissions and the potential for a runaway climate catastrophe. It's a world that once may have been habitable, but that has now become a hellish landscape of scorching temperatures and toxic atmosphere. It's often called Earth's twisted sister, a planet that shares many similarities with our own, but that has followed a dramatically different evolutionary path. Understanding why Venus became so different from Earth is crucial for preventing a similar fate from befalling our own planet, because it is so similar in size, mass, and composition. This makes Venus an ideal control group for studying the factors that influence planetary habitability. By comparing Venus to Earth, scientists can isolate the key differences that have led to their divergent fates. In its youth, it may have been a temperate world, a lush and verdant paradise with flowing rivers, sparkling lakes, and perhaps even teeming with life. Imagine a Venus with blue skies and gentle breezes, a world where liquid water flowed freely across the surface, with liquid water oceans, a paradise lost. A world that once held the potential for life, now a barren and desolate wasteland. The story of Venus is a reminder that habitability is not a guarantee, and that even seemingly stable planetary environments can be vulnerable to dramatic change. But its proximity to the sun triggered a runaway greenhouse effect, a catastrophic warming event that transformed the planet into the hellish world we see today. The increased solar radiation caused more water to evaporate, leading to a buildup of water vapor in the atmosphere. As its oceans evaporated, the water vapor acted as a potent greenhouse gas, trapping even more heat and accelerating the warming process. This created a positive feedback loop that spiraled out of control. Water vapor, a potent greenhouse gas, filled the atmosphere, creating a thick blanket that trapped solar radiation and prevented heat from escaping into space. The atmosphere became increasingly dense and opaque, further exacerbating the warming effect, trapping more and more heat. The surface temperature soared to hundreds of degrees Celsius, hot enough to melt lead. The oceans boiled away completely, leaving behind a dry and desolate landscape. This created a vicious feedback loop, a self-reinforcing cycle of warming that ultimately led to the planet's demise. The more the planet warmed, the more water evaporated, and the more water vapor filled the atmosphere, leading to even more warming. That boiled the planet dry and baked its surface, transforming it into a volcanic wasteland. The intense heat triggered widespread volcanic activity, releasing even more greenhouse gases into the atmosphere and further accelerating the warming process, leaving behind a crushing, toxic atmosphere composed primarily of carbon dioxide and laced with sulfuric acid clouds. The atmospheric pressure is so intense that it would crush a human being instantly. The surface is shrouded in a perpetual haze, making it impossible to see the stars from the ground. Studying Venus helps us model the tipping points in a planet's climate, the critical thresholds beyond which irreversible changes occur. By understanding these tipping points, we can better predict the potential consequences of our own actions and take steps to prevent a similar catastrophe from happening on Earth, providing invaluable insights into the long-term consequences of greenhouse gases in our own atmosphere. It serves as a stark reminder that even small changes in atmospheric composition can have dramatic and irreversible effects on a planet's climate. The lessons learned from Venus are crucial for informing our efforts to mitigate climate change and protect the future of our planet. Mars, on the other hand, presents a different kind of mirror, reflecting a world that once held promise but ultimately failed to sustain its habitability. It's a story of loss, of a planet that once had the potential for life, but that has now become a cold and desolate desert. It shows us a world that once had the ingredients for life: liquid water, a thick atmosphere, and a magnetic field to protect it from harmful solar radiation. Imagine a Mars with flowing rivers, vast lakes, and perhaps even simple organisms thriving in its ancient waters, but lost them. The story of Mars is a cautionary tale about the fragility of planetary habitability and the importance of maintaining the conditions that allow life to flourish. It's a reminder that even seemingly stable planetary environments can be vulnerable to dramatic change. Evidence carved into its surface tells a clear story, a compelling narrative of a planet that once teemed with water, but that has now become a dry and desolate wasteland. The geological features of Mars are like pages in a book, each one revealing a piece of the planet's past, of a warmer, wetter past, a time when Mars was a much more hospitable place than it is today. The evidence for this past is abundant, from the ancient riverbeds and lake basins to the mineral deposits that could only have formed in the presence of liquid water. With vast river networks, intricate systems of channels that once carried water across the Martian landscape. These river networks are a testament to the planet's wetter past and provide compelling evidence that Mars was once a much more Earth-like world. Sprawling deltas, fan-shaped deposits of sediment that formed where rivers emptied into lakes or oceans. These deltas are rich in minerals and organic molecules, making them prime targets for the search for ancient life on Mars, and maybe even a northern ocean. Some scientists believe that the northern lowlands of Mars were once covered by a vast ocean, a body of water that could have supported a wide range of life. But Mars was too small. Its smaller size meant that it cooled down more quickly than Earth, leading to a series of events that ultimately doomed the planet. Its core cooled, its magnetic field vanished, leaving the planet vulnerable to the harsh solar wind. Without a magnetic field to deflect the charged particles from the sun, the atmosphere was gradually stripped away into space, and the solar wind stripped away most of its atmosphere. As the atmosphere thinned, the planet lost its ability to retain heat, and the surface temperature plummeted. The planet froze, its remaining water locked away in ice caps and subsurface permafrost. The once flowing rivers and lakes disappeared, replaced by a barren and desolate landscape, becoming the cold, arid world we see today. A planet where the average temperature is well below freezing, and where the only signs of water are the ice caps at the poles and the occasional frost on the surface. Mars is a planetary fossil, a relic of a bygone era when it was a much more hospitable place. It's a world that preserves clues about how a planet can lose its habitability and what factors are essential for maintaining a life-sustaining environment. Preserving clues about how a world can lose its habitability. By studying the geological features of Mars, scientists can piece together the story of its past and understand the processes that led to its demise. The search for ancient life on Mars is therefore not just a search for extraterrestrial organisms, but also a quest to understand the conditions that are necessary for life to arise and persist. It's a search for our own origins, a quest to understand our place in the universe, is therefore a search for a second genesis, a test of whether life can arise independently on different planets. If life did arise on Mars, it would suggest that life is a common phenomenon in the universe, a test of whether life is a common outcome on worlds where conditions are right, even if only for a time. The discovery of ancient life on Mars would revolutionize our understanding of biology and our place in the cosmos. On worlds where conditions are right, even if only for a time, it would suggest that the universe is teeming with life and that we are not alone. It would also provide valuable insights into the conditions that are necessary for life to arise and persist, helping us to identify other potentially habitable planets in our galaxy. Even Mercury, the smallest and seemingly simplest of the inner planets, a world that appears to be little more than a barren rock orbiting close to the Sun, holds surprising secrets and offers profound lessons about planetary formation and evolution. Despite its small size and proximity to the Sun, Mercury has a unique and complex history that challenges our understanding of planetary science. Its enormous iron core and thin mantle are unlike anything else in the solar system, raising questions about how this planet formed and evolved. The size of Mercury's core is disproportionately large compared to its mantle, suggesting that something unusual happened in its past. Challenge our models of planetary formation, forcing scientists to rethink their theories about how planets are assembled from the protoplanetary disk. The unusual composition of Mercury suggests that it may have formed in a different region of the solar system than the other inner planets, suggesting a history of a cataclysmic impact, a collision with another large object that stripped away much of its outer layers. This impact could explain the planet's thin mantle and its unusually large iron core that stripped away its outer layers. The surface of Mercury is heavily cratered, providing further evidence of a violent past. These craters are a testament to the intense bombardment that the planet has endured over billions of years. Missions have revealed unexpected volatile materials, like water ice, hidden in permanently shadowed craters near its poles. The discovery of water ice on Mercury was a major surprise, as it was previously thought that the planet was too hot for ice to exist, hiding in permanently shadowed craters at its poles, where the sun never shines and temperatures remain extremely low. These craters act as cold traps, preserving the water ice for billions of years, defying its reputation as a completely scorched world. The presence of water ice on Mercury suggests that the planet may have once had a more substantial atmosphere, and that it may have even been habitable at some point in its past. By studying these extreme cases, the planets that have deviated most dramatically from Earth's evolutionary path, we can gain a better understanding of the factors that have made our planet so unique and habitable. The runaway furnace of Venus, a world consumed by a runaway greenhouse effect, serving as a warning about the dangers of unchecked climate change. The frozen desert of Mars, a planet that once had the potential for life, but that has now become a cold and desolate wasteland, teaching us about the importance of maintaining a stable atmosphere and a magnetic field. And the iron-hearted Mercury, a planet with an unusually large iron core, challenging our understanding of planetary formation and evolution. We can better define the precise set of conditions that are necessary for a planet to be habitable, the factors that determine whether a world can support liquid water, a stable atmosphere, and ultimately life. That allowed Earth to not only form, but to thrive, to maintain its habitability for billions of years, and to become a haven for life, transforming it from a simple rock into a complex, living planet. A planet teeming with life, a vibrant and diverse biosphere that is constantly evolving and adapting to its environment. The study of other planets is ultimately a quest to understand our own origins and to safeguard the future of our precious home. Our exploration will be a systematic journey outward from the Sun, a carefully orchestrated voyage through the inner reaches of our solar system. We will embark on a quest to understand the unique characteristics of each planet, the forces that shape them, and the potential they hold for revealing the secrets of the universe. This isn't just a sightseeing tour, it's a scientific expedition, a quest for knowledge, and a chance to ponder our place in the cosmos. We'll be using the latest scientific data and visualizations to bring these distant worlds to life, offering you an unprecedented glimpse into their alien landscapes and complex systems. Prepare to be amazed by the sheer diversity and wonder that awaits us as we venture beyond our familiar Earth. a grand tour of the inner solar system's most fascinating and enigmatic worlds. We'll be diving deep into the geology, atmosphere, and potential habitability of Mercury, Venus, Earth, and Mars. Each planet presents a unique set of challenges and opportunities for scientific discovery. From the scorching heat of Mercury to the frozen plains of Mars, we'll explore the extremes of planetary environments. We'll examine the evidence for past or present life, the processes that have shaped these worlds over billions of years, and the lessons they hold for understanding our own planet's future. This journey will be a testament to human curiosity and our relentless pursuit of knowledge about the universe we inhabit. We'll begin where the sun's influence is most ferocious, where the solar wind relentlessly bombards the surface and temperatures soar to unimaginable heights. This is the realm of Mercury, the innermost planet, a world perpetually locked in a dance with our star. Here, we'll witness the raw power of the sun and its profound impact on a planetary body. We'll explore the challenges of surviving in such an extreme environment and the unique adaptations that Mercury has developed to withstand the sun's relentless energy. Right at the doorstep of our star, Mercury's proximity to the sun makes it a crucial laboratory for understanding the dynamics of star-planet interactions. Its highly elliptical orbit and unique rotational period create a bizarre day-night cycle unlike anything else in the solar system. We'll delve into the mysteries of Mercury's formation and evolution, exploring the theories that explain its unusually large iron core and its surprisingly volatile, rich surface. Our first stop is Mercury, the iron world. A planet of stark contrasts and hidden secrets, Mercury presents a unique challenge to our understanding of planetary formation and evolution. Its heavily cratered surface tells a story of intense bombardment, while its surprisingly strong magnetic field hints at a dynamic interior. We'll unravel the mysteries of this enigmatic world, exploring its unique features and the processes that have shaped it over billions of years. Here, we'll witness a landscape of extremes, a testament to the harsh realities of the inner solar system. Mercury's surface is a mosaic of ancient craters, vast plains, and towering cliffs, each telling a story of impacts, volcanism, and tectonic activity. We'll explore the geological history of this world, piecing together the events that have shaped its unique and unforgiving terrain. A planet of fire and ice, where a single day lasts longer than its year. The extreme temperature variations on Mercury, ranging from scorching heat to frigid cold, are a direct result of its slow rotation and lack of atmosphere. This creates a world of dramatic contrasts, where the sun-baked surface can reach temperatures of over 400 degrees Celsius, while the permanently shadowed craters harbor ice deposits. We'll examine the mechanisms that drive these extreme temperature swings and the implications for the planet's surface processes. We'll glide over its ancient, heavily cratered surface, a journey through time etched in stone. As we soar above the landscape, we'll witness the scars of countless impacts, each a reminder of the solar system's violent past. We'll explore the different types of craters, from the small and pristine to the large and degraded, and learn about the forces that created them, a testament to the solar system's violent youth. The bombardment that shaped Mercury's surface was a common occurrence in the early solar system, as leftover debris from the planet formation process rained down on the newly formed worlds. By studying the craters on Mercury, we can gain insights into the size and frequency of these impacts and their effects on the planet's evolution. This is a window into the past, a glimpse of the chaotic conditions that prevailed in the early solar system. We'll explore the discoveries from missions like Messenger, a dedicated spacecraft that spent years orbiting Mercury and gathering unprecedented data about its surface, atmosphere, and magnetic field. Messenger's observations revolutionized our understanding of Mercury, revealing a world far more complex and dynamic than previously imagined. We'll delve into the key findings of this mission and the insights they provide into the planet's history and evolution, which unveiled a world far more complex than we ever imagined, challenging our preconceived notions about planetary formation and evolution. Messenger's high-resolution images revealed a surface sculpted by volcanism, tectonics, and impacts, while its measurements of Mercury's magnetic field and atmosphere provided clues about its internal structure and composition. We'll examine the evidence for these processes and their role in shaping the planet we see today, with a surprising magnetic field and strange, hollowed-out terrains. Mercury's magnetic field is particularly intriguing, as it is much stronger than expected for a planet of its size and slow rotation. The hollows, on the other hand, are shallow, irregular depressions found across the planet's surface, and their origin remains a mystery. We'll explore the theories that attempt to explain these unique features and their implications for our understanding of Mercury's internal processes. From the sun-scorched plains of Mercury, vast expanses of relatively smooth terrain that cover a significant portion of the planet's surface, we'll travel to our nearest planetary neighbor, a world shrouded in clouds and mystery, a stark contrast to the barren landscape of Mercury. A world shrouded in mystery and menace. Venus, with its thick, toxic atmosphere and scorching surface temperatures, presents a formidable challenge to exploration. Its dense cloud cover obscures the surface from view, making it difficult to study its geology and composition. Yet, despite these challenges, Venus holds valuable clues about the evolution of terrestrial planets and the potential for runaway climate change. Our second stop is Venus, Earth's twisted sister. A planet of similar size and composition to Earth, Venus followed a dramatically different evolutionary path, resulting in a hellish environment unlike anything on our own planet. We'll explore the factors that led to this divergence, examining the role of volcanism, atmospheric processes, and the runaway greenhouse effect. We'll pierce its thick perpetual veil of sulfuric acid clouds, a dense and corrosive atmosphere that blankets the entire planet, trapping heat and creating a surface environment hostile to life as we know it, to glimpse a surface hidden from human eyes for millennia. Radar imaging has allowed us to penetrate the cloud cover and reveal the hidden landscape of Venus, a world of vast plains, towering volcanoes, and ancient lava flows. We'll explore the geological features of Venus, examining the evidence for past and present volcanic activity and the processes that have shaped its surface over billions of years. Here, we'll find a world crushed by an atmosphere 90 times denser than Earth's, a suffocating blanket of carbon dioxide that exerts immense pressure on the surface. This extreme pressure makes it difficult for spacecraft to survive for long, limiting our ability to explore the planet up close, and baked by surface temperatures hot enough to melt lead. The extreme heat on Venus is a result of the runaway greenhouse effect, where the dense atmosphere traps solar radiation and prevents it from escaping back into space. This has created a surface environment where temperatures can reach over 460 degrees Celsius, hot enough to melt lead and make it impossible for liquid water to exist. We'll learn about the runaway greenhouse effect, a phenomenon that transformed Venus from a potentially habitable world into a planetary inferno. By studying the processes that led to this runaway effect, we can gain valuable insights into the factors that control planetary climates and the potential for similar events to occur on Earth, that turned a potential paradise into a planetary inferno, a cautionary tale about the delicate balance of planetary climates and the potential consequences of unchecked greenhouse gas emissions. Venus serves as a stark reminder of the importance of understanding and mitigating the effects of climate change on our own planet, and examine the tantalizing hints of active volcanism, suggesting that Venus may still be geologically active despite its seemingly dormant surface. Evidence for recent volcanic eruptions has been found in the form of transient increases in sulfur dioxide levels in the atmosphere and radar images of fresh lava flows, captured by the few hardy probes that have dared to land on its hostile ground. The Soviet Venera missions were the only spacecraft to successfully land on Venus and transmit images back to Earth. These probes endured extreme temperatures and pressures for a short period before succumbing to the harsh environment, providing us with invaluable glimpses of the Venusian surface. Next, we'll return home, leaving behind the scorching landscapes of Venus and setting our sights on the familiar blue marble that is our own planet. To view our own planet from a cosmic perspective. From the vantage point of space, Earth appears as a vibrant and fragile oasis, a unique world teeming with life. This perspective allows us to appreciate the interconnectedness of our planet's systems and the importance of protecting its delicate balance. Our third destination is Earth, the living planet. A world unlike any other in our solar system, Earth is home to a vast array of life forms, from microscopic bacteria to towering trees and complex animals. Its unique combination of factors has allowed life to not only emerge, but to thrive and shape the planet in profound ways. We'll see it as the astronauts do, those privileged few who have had the opportunity to witness Earth from the vastness of space, gaining a profound appreciation for its beauty and fragility. A vibrant blue oasis in the blackness of space. Earth's abundant liquid water, its protective atmosphere, and its stable climate make it a haven for life in a solar system filled with barren and hostile worlds. We'll explore the unique combination of factors, the delicate interplay of geological, chemical, and biological processes, liquid water, essential for all known forms of life, covering over 70% of the Earth's surface and playing a crucial role in regulating its climate. A protective atmosphere shielding us from harmful solar radiation and regulating the planet's temperature, a dynamic crust constantly reshaped by tectonic activity, creating mountains, volcanoes, and ocean trenches, and a global magnetic shield, deflecting harmful solar wind and cosmic rays, protecting our atmosphere and life on Earth, that allowed life to not only emerge but to flourish, diversifying into a vast array of forms and adapting to a wide range of environments and fundamentally reshape an entire world. Life has transformed Earth's atmosphere, oceans, and land surface, creating a complex and interconnected biosphere that sustains all living things. We'll trace the story of how this planet became a self-regulating system, a complex web of interactions between the atmosphere, oceans, land, and life, a complex interplay of geology, chemistry, and biology that maintains a stable and habitable environment for life to thrive, that has maintained its habitability against all odds for billions of years, a testament to the resilience and adaptability of life on Earth. A true anomaly in our solar system. Earth's unique combination of factors makes it a truly special place, a haven for life in a universe that seems largely devoid of it. Our final destination in this tour of rocky worlds, a journey through the inner solar system's most intriguing planets, will be the most alluring target for future exploration. Mars, with its potential for past or present life, its intriguing geological history, and its relatively accessible environment, is the next frontier for human exploration. We'll journey to Mars, the red enigma. A planet of contrasts, Mars is both familiar and alien, a world that holds clues to the past and potential for the future. Here we'll wander through the largest volcano and the deepest canyon in the solar system, Olympus Mons and Valles Marineris, colossal geological features that dwarf anything on Earth, testaments to a geologically active past. These features provide evidence of a time when Mars was a much more dynamic and volcanic world than it is today. We'll follow the ghostly tracks of ancient rivers, dried-up channels that once carried liquid water across the Martian surface, and stand on the shores of long-vanished lakes, remnants of a time when Mars was warmer and wetter, potentially capable of supporting life, piecing together the evidence of a once watery world. The presence of ancient riverbeds, lakebeds, and other water-related features suggests that Mars may have once been a much more habitable planet than it is today. We'll join the robotic rovers and orbiters in their ongoing search for biosignatures, the telltale signs of past or present life, the chemical fingerprints of ancient life, hidden within the Martian rocks and soil, waiting to be discovered. As we confront the ultimate question, the question that has driven human exploration for centuries, are we alone? Is life a unique phenomenon confined to Earth, or is it a more common occurrence in the universe? Mars beckons with the promise of answers, a world that may hold the key to understanding the origins and distribution of life in the cosmos. A world of lost potential that holds the key to understanding life's place in the universe. Mars, once a potentially habitable planet, now stands as a testament to the fragility of life and the importance of understanding the factors that make a planet habitable. Its secrets may hold the key to our own survival and our understanding of our place in the vast expanse of the cosmos. Our journey through the inner solar system is not just about looking back at our origins, at the formation of the planets we know so well. It's not simply a historical expedition to understand how our own cosmic neighborhood came to be. It's a crucial foundation upon which we build our understanding of the universe at large. We delve into the past to illuminate the future, using the lessons learned from our planetary siblings to guide our exploration of the vast unknown. It's also about looking outward to the countless worlds beyond, to the swirling nebulae and distant suns that cradle potentially habitable planets. It's about expanding our horizons and daring to imagine the possibilities that lie beyond our solar system's familiar embrace. The quest to understand exoplanets is a testament to human curiosity, a drive to explore the uncharted territories of space and uncover the secrets they hold. In recent decades, a revolution has taken place in astronomy, a paradigm shift that has forever altered our perception of the cosmos. We've moved from a singular understanding of our own solar system to the realization that planets are commonplace throughout the galaxy. This revolution has been fueled by technological advancements, innovative research, and the unwavering dedication of scientists around the world. We've discovered thousands of planets orbiting other stars, known as exoplanets, each one a unique and fascinating world waiting to be explored. These discoveries have shattered our preconceived notions about planetary systems and revealed the incredible diversity that exists beyond our own. From gas giants to rocky worlds, exoplanets come in all shapes and sizes, challenging our understanding of planet formation and evolution. This cosmic census has revealed a stunning diversity of worlds, a breathtaking array of planetary bodies that defy easy categorization. We found planets orbiting multiple stars, planets with eccentric orbits, and planets that are tidally locked to their host stars. The sheer variety of exoplanets is a testament to the complex and dynamic processes that shape planetary systems, from hot Jupiters orbiting their stars in a matter of days, scorching gas giants that hug their parent stars in incredibly tight orbits. These extreme worlds challenge our understanding of planetary migration and the forces that shape the architecture of planetary systems. Their existence raises questions about the conditions necessary for planet formation and the potential for habitability in such extreme environments, to rocky super-Earths that may be even more geologically active than our own planet, potentially harboring vast oceans, towering volcanoes, and dynamic tectonic plates. These super-Earths offer a glimpse into the possibilities of planetary evolution and the potential for life to arise on worlds that are significantly different from our own. They represent a tantalizing target in the search for habitable environments beyond Earth. We're no longer limited to the 4 rocky worlds in our backyard, the familiar planets that have shaped our understanding of planetary science for centuries. While these planets remain crucial benchmarks, they represent only a tiny fraction of the planetary diversity that exists in the universe. We now have a galaxy full of planets to study, a vast and diverse collection of worlds that offer unprecedented opportunities for comparative planetology. Each exoplanet is a unique laboratory, providing valuable insights into the processes that govern planet formation, evolution, and habitability. This explosion in exoplanet discovery has transformed comparative planetology from a local science into a galactic one, expanding the scope of our investigations from our solar system to the entire Milky Way galaxy and beyond. We can now compare and contrast planets across vast distances, searching for patterns and trends that reveal the underlying principles of planetary science. The fundamental principles we learn from Mercury, Venus, Earth, and Mars, the lessons gleaned from their unique histories and characteristics, are our primary tools for interpreting these distant worlds, for deciphering their secrets, and understanding their potential for habitability. These 4 planets serve as a crucial Rosetta Stone, allowing us to translate the faint signals we receive from exoplanets into meaningful insights about their composition, atmosphere, and potential for life. When astronomers detect a rocky exoplanet orbiting its star in the habitable zone, that sweet spot where liquid water could potentially exist on the surface, what does that really mean? What are the factors that truly determine whether a planet is habitable, and how can we identify them from afar? Our own solar system teaches us that location is not enough. that simply residing within the habitable zone does not guarantee a life-friendly environment. Other factors, such as atmospheric composition, geological activity, and the presence of a magnetic field, play a crucial role in determining a planet's habitability. A world in the right place could be a toxic pressure cooker like Venus, shrouded in a thick, suffocating atmosphere of carbon dioxide, with surface temperatures hot enough to melt lead. Venus serves as a stark reminder that a planet's atmosphere can dramatically alter its habitability, even if it resides within the habitable zone. Or a frozen desert like Mars, with a thin, tenuous atmosphere and a frigid surface where water exists primarily as ice. Mars highlights the importance of atmospheric pressure and temperature in maintaining liquid water on a planet's surface, a key ingredient for life as we know it. Understanding our neighbors helps us refine the concept of habitability to move beyond simple definitions based on distance from a star and incorporate a more nuanced understanding of the complex interplay of factors that determine a planet's suitability for life, and build more sophisticated models to predict which of these distant worlds might actually be Earth-like, possessing the right combination of factors to support liquid water, a stable climate, and potentially even life. These models incorporate data from our own solar system, as well as observations of exoplanets, to create a more comprehensive picture of planetary habitability. The 4 inner planets provide us with essential templates for what is possible, a range of potential outcomes for rocky planets that can help us interpret the characteristics of exoplanets. They offer a framework for understanding the factors that influence planetary evolution and the potential for habitability. They represent 4 potential outcomes for a rocky planet's evolution, 4 different paths that a planet can take depending on its initial conditions and the processes that shape its development over billions of years. By studying these different outcomes, we can gain a better understanding of the factors that determine a planet's ultimate fate. Is an exoplanet small and dense like Mercury, suggesting a stripped mantle, a history of intense bombardment, or a unique formation process? Understanding the density and size of an exoplanet can provide clues about its composition and its evolutionary history. Does its atmosphere show signs of runaway carbon dioxide, like Venus, indicating a history of volcanic activity and a lack of effective carbon sequestration? The presence of carbon dioxide in an exoplanet's atmosphere can provide insights into its geological activity and its potential for a greenhouse effect. Or does it show hints of a thin, cold atmosphere like Mars, suggesting a loss of atmospheric pressure and a potential for surface water to freeze? The density and composition of an exoplanet's atmosphere can reveal clues about its past climate and its potential for habitability. The light from these distant stars, filtered through the atmospheres of their planets, as the planets transit in front of their stars, carries chemical fingerprints, subtle spectral signatures that reveal the composition of the gases present in the exoplanet's atmosphere, that telescopes like the James Webb Space Telescope can analyze, using sophisticated instruments to dissect the light and identify the elements and molecules present in the exoplanet's atmosphere. By comparing these fingerprints to the atmospheric profiles of Venus and Mars, by drawing parallels and identifying key differences, we can begin to characterize these worlds, to understand their atmospheric composition, their potential for a greenhouse effect, and their overall habitability, and prioritize the most promising candidates in the search for life, focusing our resources on the exoplanets that exhibit the most compelling signs of habitability and the potential for harboring life. Ultimately, the study of our own inner solar system, the detailed examination of Mercury, Venus, Earth, and Mars, is the foundation for one of humanity's most profound quests, the search for life beyond Earth, the search for another Earth, a planet that shares our characteristics and can potentially harbor life. Before we can confidently identify a pale blue dot orbiting a distant star, a faint glimmer of light that signals the presence of a potentially habitable world, we must first understand the full story of the dots in our own cosmic neighborhood, the planets that share our solar system and have shaped our understanding of planetary science. The trials and tribulations of Mercury, Venus, and Mars, their successes and failures in the planetary evolution, provide the context, the warnings, and the guideposts for this search, helping us to navigate the complexities of exoplanet characterization and identify the most promising candidates for life. They teach us what to look for, the key indicators of habitability that can be detected from afar, and what pitfalls might prevent a promising world from becoming a living one, the factors that can lead to a planet's demise and render it uninhabitable. Our journey through these worlds of rock and fire, through the diverse landscapes and extreme environments of the inner solar system, is therefore the first essential step in a much larger journey, a cosmic voyage to explore the vast expanse of the universe and search for life beyond Earth, to understand our place in the cosmos, to unravel the mysteries of the universe and discover our connection to the grand tapestry of existence, and to find out if, somewhere out there, amidst the countless stars and galaxies, another world has followed Earth's remarkable path, a planet that has defied the odds and emerged as a haven for life. When we look beyond the rocky surfaces of the inner planets, another story unfolds. A tale told not by planets themselves, but by their companions, the moons. Among the 4 terrestrial worlds, only 2 are graced with natural satellites, Earth and Mars. But these moons are as different as the planets they orbit, and their presence or absence has shaped the destinies of their parent worlds in profound ways. Earth's moon is an anomaly in our solar system, a colossal satellite nearly a quarter the size of its planet. Its origins trace back to a cataclysmic collision in the early days of the solar system, when a Mars-sized body struck the young Earth. The debris from this impact coalesced, forming the moon we know today. But our moon does far more than light up the night sky. Its gravitational pull stabilizes Earth's axial tilt, preventing wild swings in climate that could have made the evolution of complex life far more difficult. The moon's tidal forces have shaped our oceans, driven the rhythms of life, and may have even played a role in the emergence of life itself, creating tidal pools where the first building blocks assembled. Mars, by contrast, is orbited by 2 tiny irregular moons, Phobos and Deimos. Unlike our moon, these are not the remnants of ancient collisions, but likely captured asteroids from the nearby asteroid belt. Their lumpy shapes and chaotic orbits tell a story of cosmic chance rather than planetary design. Phobos, the larger of the 2, is on a doomed path, slowly spiraling inward, destined one day to break apart or crash into Mars. Deimos, drifting farther away, is less threatened, but neither moon has had a stabilizing effect on Mars's tilt or climate. Without a large moon, Mars's axis wobbles dramatically over time, contributing to the planet's harsh and variable climate. But what of Mercury and Venus? These worlds are moonless, and their loneliness is no accident. Their proximity to the Sun means that any would-be moons would have been destabilized by the Sun's powerful gravity, ultimately falling into the planet or escaping into space. Moreover, the violent history of planetary formation in the inner solar system left Mercury and Venus with little chance to capture or retain satellites. Their lack of moons has left them without the stabilizing influences enjoyed by Earth, and in Venus's case may have contributed to its wild rotational axis and extreme climate. The moons of the inner planets, whether mighty, modest, or missing, offer a window into the forces that shape worlds. They remind us that the story of a planet is not written by its surface alone, but by the companions it keeps, the cosmic accidents that shape its evolution, and the delicate balances that can tip the scales between chaos and stability, lifelessness, and the potential for life. As we continue to unravel the mysteries of the inner planets, each new mission becomes a key that unlocks another chapter in the epic story of our solar system. The coming years promise a renaissance of exploration. Robotic emissaries are poised to brave the inferno of Venus, seeking answers to how a once Earth-like world became so hostile. On Mars, rovers and orbiters dig deeper into the planet's ancient past, searching for the fingerprints of water and perhaps life itself. And closer to home, the moon is once again in our sights, not just as a destination, but as a proving ground for humanity's next giant leap. These missions aren't just about distant worlds, they're mirrors reflecting our own planet's history and fate. By studying Venus's runaway greenhouse effect, we gain vital lessons about climate change and the delicate balance that sustains life on Earth. By probing Mars's lost rivers and vanished atmosphere, we glimpse what might have been and what could still be if we fail to steward our home. But the significance of this exploration goes beyond data and discovery. It's a reminder of our place in the cosmos, a fragile oasis in a vast and indifferent universe. Understanding the destinies of our planetary neighbors deepens our appreciation for Earth's rare habitability and challenges us to protect it. As we reach for other worlds, we are reminded, again and again, that our greatest adventure may be understanding and preserving the one world we already call home. Before you go, if you enjoyed this journey through the cosmos, please like this video, share it with fellow space enthusiasts, and leave a comment below to share your thoughts or questions. The Physics and Cosmos Academy is dedicated to bringing you high-quality documentaries on space physics, astrophysics, and cosmology. Subscribe to our channel to stay updated with future explorations of neutron stars, black holes, the Big Bang, dark matter, dark energy, and other mysteries of the universe. Your support helps us continue to explore the wonders of space together.